Hey friends, it has been again. This is a video for the vector calculus class, and we are going to take a look at parametric surfaces. This may be the longest video of the semester because I'm going to try to give you plenty of examples of this, okay? And then with regard to saying that, it occurs to me that I should have opened up a bunch of windows that I may be going to share with you and have done a bunch of graphs ahead of time. And as you might guess, I didn't. So we'll just see how this goes. All right. So when we talk about parametric surfaces, what you need to think about sort of structurally is that if you have a curve, it is a one-dimensional sort of thing. It is determined by one choice, one variable. So if you have something that is living on the plane, you may have x equals a function of t and y equals a function of t. It may seem like there's three variables there, but only one of them is the independent variable, okay? If you were looking at a line or curve on the plane that was given to you by y equals a function of x or some combination of x's and y's, the thing that you've got going on is that there are two variables, but one equation, which removes one of your choices, okay? And so that means that you only have one choice left. It's something one-dimensional. Whereas if you do something parametric on the plane, it seems like you've got three variables. You will have two equations, x equals a function of t, y equals a function of t. And so the two equations remove two of your choices, okay? So when we look at parameterizing surfaces, we are going to think about having two variables that are choices. And then your x and your y and your z are going to be determined by those two variables. I'll usually use s and t or u and v or r and theta or who the hell knows, okay? But there's a place that you need to start with from this of realizing that if we're parameterizing, there's a reason for parameterizing. If we could accomplish everything by just saying z equals f of x, y, then we would just do that. And we wouldn't ever bother with any of this parametric crap, you know? So try not to approach every problem by just plugging in x equals u, y equals v, and then z equals whatever the hell it turns out to be. Sometimes that works. Maybe even a lot of times that works. But there's cases where it doesn't. In particular, if you're talking about circles, parameterize them with sine and cosine. If you're talking about hyperbolas, parameterize them with hyperbolic sine and cosine, okay? So I prepared a little kind of a sheet here, and if I can find my mouse again, I will share with y'all, assuming that the screen wants to mirror this morning. 1, 2, 3, go. Yay, it's going to mirror. All right. So this is just a little bit of a primer here on your parametric surfaces. So if you've got z equals f of x, y, lots of times you can parameterize it just by saying, I'm going to have x and y be my parameters, and then do this f of x, y. Likewise, if you had y equals f of x, z, or if you had x equals f of y, z, you could do something similar, okay? Now, if we're going to talk about parameterizing a plane, I think this starts to illustrate the sort of thing that we have to think of doing. If you've got a plane, and then you can identify one point on it and identify two directions to go in. Ideally, those directions would be orthogonal to each other, because if they're orthogonal, it makes it a really efficient way to represent these things. But they don't have to be orthogonal. In fact, if you look back historically, I'm sorry, I'm going to go off on a tangent, historically, and you talk about Cartesian coordinates. Well, the Cartesian coordinates were developed by René Descartes. They are perpendicular to each other, but at the same time, Pierre de Fermat, the guy from Fermat's last theorem, was also looking at a different way of doing Cartesian coordinates, and he saw no reason to make them perpendicular to each other. So Cartesian coordinates won out because they're easier to work with. But now, if I want to have any other point on the plane, maybe this over here, Q, then I can go from P, some multiple of V, or maybe it's a multiple of V plus a multiple of Q, and that is the reason why we do this SU and TV, okay? So, yeah, I will look at an example here in a minute where we're doing that sort of thing. And we'll look at an actual picture of it. But if you want to do an ellipse, and this is a curve, right? So any sort of ellipse, you can identify two directions like that and just multiply cosine theta and sine theta by that u and that v. And as the theta goes from 0 to 2 pi, it's going to then transcribe a circle in the plane determined by u and v, right? The reason why that works out for parameterizing is this nice thing here of cosine squared plus sine squared equals 1. And then that is similar to having an equation, x squared plus y squared equals 1. Now, if you want a different radius, and in particular, if you want it to be an ellipse and have radii pointing in other directions, then you want to have some coefficients going on here and so forth. But that's a little beyond what we're really going to try to talk about. Okay, so just in general, ellipses are going to be parameterized with identify two vectors and multiply them by sine and cosine. Hyperbolas, on the other hand, have equations like x squared minus y squared equals 1. And the hyperbolic sine and cosine have the property that they obey that sort of equation, okay? So likewise, if you are going to do something that's a hyperbola, then you can talk about the u and v directions and multiply by hyperbolic cosine and hyperbolic sine, okay? The thing that you need to spot, though, is that hyperbolic cosine of t is always going to be greater than or equal to 1, whereas the hyperbolic sine of t is going to go to negative infinity and positive infinity. I guess really I ought to have written this. Is that right? Yeah, okay. I'm going to write that. And in my head, I'm thinking, yeah, that's right. Okay. So, so in any case, though, when you're doing this parameterization and you need to think about doing a leaf of a hyperbola, if the hyperbola is opening out there in the x direction, that means that the x part is always greater than or equal to 1 or whatever it is that you're working with. And so that's why that one would have the cosh in the x direction. And because it needed to go up and down forever, it would have the sinh in the y direction. Okay. All right. So we're going to do some quick parameterizations here, and then maybe I'll jump over to Desmos and graph them real quick to show what's going on. So with regard to this first one, you can see that the coefficients of x squared and y squared are both positive, and that suggests that we're going to have something that's an ellipse, right? If one of them is positive and one is negative, then you're going to have something that's a hyperbola. So for our purposes here, we're going to have to do some completing the square. So I'm going to just reserve a little bit of room to do this. And I can see with the 2x squared and the 12x, if I factor out the 2, then I have a minus 6x. And the 12y, I'll factor out the 3 and have a plus 4y. So to complete this square, I have to add 9. And that means on the other side, I have to add 18. And to complete this square, I have to add 4. And that means on the other side, I have to add 12. So that means I have 2 times x minus 3 squared plus 3 times y plus 2 squared is equal to 36. So if I go ahead and divide there, then I will have x minus 3 squared divided by 18 plus y plus 2 squared divided by 12, okay, is equal to 1. Now I've forced it into the form where it looks like cosine squared plus sine squared equals 1. So now I'm going to let my x minus 3 over the square root of 18. Let's see, that's 3 square roots of 2. That's going to be cosine theta. And then I'm going to let the y plus 2 over, let's see, that's 2 square roots of 3. It's going to be the sine of theta. So if I solve there, and I realize that I should not have shoved 2 of these onto one page, I'll try to fix that in the notes that I give you all though. But if I solve for the x there, I will end up with 3 minus 3 root 2 cosine theta. And the y, I will end up with a minus 2 root 3 sine theta. Okay. Now the plus or minus on sine and cosine aren't going to matter so much because of the fact that we are going to have sines and cosines, and those will go all the way from -1 to +1. But I am, as promised, going to jump over here to Desmos, and I am going to go ahead and type in there a parenthesis, and then my x was 3 minus 3 square root of 2 cosine. I will use t instead of theta, and then minus 2 square root 3 sine theta, or sine t, okay? So you should be able to see on my graph here that I only got a little bit of a circle, but that's because my t's went from 0 to 1. I'll go from minus pi to pi, and now I get the whole circle. If I just wanted a part of the circle, then I would adjust it to be whatever particular variations that we might have there. All right. So parameterizing ellipses shouldn't be too rough. And then I'm going to take that other example that you saw, and I'm going to come back over here, and we're going to figure out how to parameterize a hyperbola. Pretty similar, okay? Screen mirroring, 1, 2, 3, touch. It really does seem like if I count to 3 beforehand that it works better. All right, so we're going to parameterize this, this hyperbola here. And like before, we're going to have to complete the square. And that means factoring some stuff out there. And so y squared minus 2y. You might have noticed that I was tricky with that and chose my numbers so they worked nicely. Sometimes your numbers don't work nice and you just have to live with it. But we're adding 4, which means we really added 8. And we're adding 1, which means we really subtracted 3. So you have 2 times x minus 2 squared minus 3 times y minus 1 squared is equal to 15 minus 3 is 12. Okay. Now, at this point, you can see that it's got the x part, excuse me, it's got the x part having a positive coefficient and the y part having a negative coefficient. Up until we got this over here to be positive, we didn't really know that for sure. This will come back to haunt us when we are doing our three-dimensional sorts of things, because we have to keep track of, believe it or not, the number of pluses and minuses to be able to tell our shapes. All right, so now if we come along here, x minus 2 over the square root of 6 needs to be cosh t, and y minus 1 over 2 needs to be sinh t. So our x is going to end up being 2 plus the square root of 6 cosh t. I am just realizing in the previous page, I screwed up my signs, my plus or minuses. And I am going to go back and fix that, but I'm not going to bore y'all by making you watch it. Okay. All right. So bear in mind that we're going to have those as a parameterizations. And then I'm going to jump over here to my Desmos in another window. And the reason that I do this, I do my Desmos on the computer screen instead of the iPad screen, is that it's just faster to type. Okay. So we had this being our x was 2 plus square root of 6 cosh t, and then our y was 1 plus 2 sinh t. Okay, and I'm going to turn off the old one, and you can see that you've just got a little section of the hyperbola like before. You want to do a symmetric interval to get a piece of it, and then you might want to go ahead and go minus 10 to 10. You really don't need very much to get a pretty wide interval. If I go from minus 5 to 5, that's going to be out of the side of where you can see. Hyperbolic sine and hyperbolic cosine are in fact going to be exponential functions. All right, now here is the thing that's going to make a difference. I'm going to put in a minus here, and and that difference of the minus or plus cosh is going to do the two pieces of it. Now there is an alternative that you can do, and I am going to paste this here. I'm going to turn these two off. All right, this one's weird because your regular circular secant and tangent have a nice relationship that looks a lot like hyperbolic cosine and hyperbolic sine. You can actually come in here and say secant t and tan t and get the same sort of thing. Now remember, you have discontinuities on those at minus pi over 2 and pi over 2. So when we say minus pi over 2 to pi over 2, we'll actually get the whole graph. But if I went ahead and had 2 cycles of it, it'll draw the other portion. So there might be an argument for why you might use the hyperbolic secant and hyperbolic tangent. I'm sorry, the secant and tangent instead of hyperbolic sine and cosine, just because you're uncomfortable with hyperbolic sine and cosine and you kind of know about secant and tangent. The problem is because of those infinite discontinuities that happen there, you may end up getting pieces that are stretched, and just sometimes it'll make the graph look weird, okay? But I want y'all to be aware that those are two options there that accomplish what we are looking to accomplish with parameterizing. And now I'm going to jump back. This is going to be a long one. I'm going to jump back to looking at the iPad. You know, there's another way to do this where I wouldn't have to jump around quite as much, but oh well. So we are going to look at parameterizing a plane. Oh, brother. So, but in particular, this is going to look at a plane region. I should have put the word region here. Okay, so we're just going to do a piece of a plane, not the whole plane. So when you take a look at these vertices that you got here, I just went and generated them in such a way that they would actually constitute a parallelogram. And it will turn out that the vector that goes from here to here and the vector that goes from here to here, if you add them together, would in fact take you to the fourth point. So in a sense, that fourth point isn't super necessary for what we need, okay? But I'm going to find my u vector by just saying, how do I get from this point to that point? And so if I'm going from -4 to -6, I had to subtract 2. If I'm going from -9 to -2, I had to add 7. If I'm going from 10 to -8, woo, I had to subtract 18. Then the other one here, I am going from -4 to -5, so I had to subtract 1. From -9 to 7, I had to add 16. And from 10 to -3, I had to subtract 13. Okay, so my parameterization, I'll use the variables s and t here because I've used u and v to mean vectors, right? But my s times the vector u plus my t times the vector v, and both s and t are going to be values between 0 and 1. And that way, if I need to go across halfway and up halfway, I can coordinate those and get, you know, a point in the middle, right? If I, instead of that, wanted to cut this in half, right? Instead of having the whole parallelogram there, I just wanted half of it. I could say I want s to be less than or equal to 1 and t to be less than or equal to 1 minus s, or flip it and do it the reverse way, okay? So there are options to actually get just pieces. And in fact, if you wanted some weirdly shaped thing, you could just replace that s with some function of s. So you can get different shapes, all right? So with regard to this, I'm going to share screen again, but instead of Desmos, I am going to, where the hell did I put that Calc plot 3D? Yep. I'm going to share with you all the Calc plot 3D. And with it, I'm going to do a parametric surface. And the parametric surface, I'm going to have to define x and y and z on. It predefines that I have to use u and v to mean the parameters here. So I am just going to go down there and remember the vectors I got were -2, 7, -18, and -1, 16, -13. So I am going to start at the point -4, minus 9, 10, and then the minus 4, I'm going to have to say minus 2u and minus 1v. I think I have to put multiplication signs here. I'm not sure, but oh, nope, I don't. Okay, whatever. Then for the y part, I started at negative 9, and I have to say plus 7u and plus 16v. And then on the z part, I started at 10, and I have to say minus 18u and minus 13v. Okay, those were randomly generated numbers and stuff. So they ended up being kind of messy. All right, and I'm going to take away that and then make it draw this. And I'll have to zoom out so that we can see the section of the parallelogram. Wow, it's fairly big there. But yeah, you can see that you've just got a parallelogram that's lying in a particular plane. Okay. So that tells you how to go about parameterizing a plane. So the surfaces we really need to take a look at are the quadric surfaces. Go to your textbook, look in the table of contents. There's a section in chapter 12, 13, I don't know, titled Quadric Surfaces. And it details these basic surfaces that all have very similar looking equations to them. And then it tells you nothing about parameterizing them, but I can show you how to parameterize them, and it's not super hard, okay? The main thing to remember is that we're going to try to look for something where it's circles and hyperbolas, okay? Just that's our goal. So let's take a look at an example. Oh, and we have to complete the square. Yeah, let's look at an example here on the iPad, and then we will try to get a graph of it. Okay, so we're parameterizing 16x squared plus 9y squared. You can read, okay? Like before, we're going to complete the square. So I'm going to come over here and say 16 times x squared. It's a minus 32x, so I have a minus 2x, and then plus 9 times the y squared. It's a minus 36y, so now I'll have a minus 4y plus 16z squared. And oh, z squared doesn't have anything, so that'll just be by itself. And I'm going to move the 36 over here. I have to add 1. That means I added 16. And then I have to add 4. That means I have to add 36. And now I have 16 times x minus 1 squared plus 9 times y minus 2 squared plus 16z squared is equal to 16. Okay, so when I divide, I will have x minus 1 squared. The 16s will cancel. I'm going to put it over 1 so that it's nice and neat. Plus y minus 2 squared over, that doesn't cancel, so I'm going to write it as 16/9, and you'll see why. And then plus z squared divided by 1 equals 1. Okay, so all of those are positive. We don't have to do anything weird. You can, in fact, treat this as though it was x squared plus y squared plus z squared equals 1. You should remember that for polar coordinates, that you could do this. Rho, man, do I remember this? Cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. Okay, we have a sphere that has a radius of 1, so we just assign rho to be 1. So now for x squared plus y squared plus z squared equals 1, we know what to let x and y and z be, okay? But we don't exactly have that. We instead have x minus 1 over 1 needs to be cosine theta sine phi. And y minus 2 over 4/3 needs to be sine theta sine phi. And well, I guess the z is all right. It's gonna be just the cosine phi. Now, I'm going to do algebra. Y'all can do that with no problem. But here's a sticker. I have to type it into something that's going to assume u and v are my parameters. So I have to change it and come to x equals 1 cosine u sine v, y equals 2 plus 4/3 sine u sine v, and z equals cosine v. And then you have to remember that the u was theta and the v was phi, okay? If you switch those around, you need to switch around your ranges there. It's just, they're set up to do that nicely, okay? If you need to have just a portion of your sphere instead, then you would make the appropriate adjustments to the ranges. All right. So now share screen, jumping back over here, and I am making x be 1 plus cosine u sine v, the y to be 2 plus 4/3 sine v, and z to be just cosine. And my u 0 to 2 pi, and my v to be 0 to pi. All right, turn it off, turn it back on. Suddenly we've got our sphere. Now you may notice that that sphere does not look very spherical. It looks kind of ellipsoidal. And I think that is just because, oh, yeah, no, that is totally appropriate, isn't it? Because the y direction that we had over here had a 4/3 times it. If we, on the other hand, had had just a 1 in there instead, and we redraw it, it looks super duper spherical, right? But we had the 4/3, and that was the reason why it looks flatter in that direction, okay? Or longer in that direction, actually. So, all right. So, coming back around here, now we're going to tackle a different surface. And so I'm sharing screen again. I am tempting fate every time I do this, I think. So, right. So this one here, you can see that you've got the positive over there on the right-hand side, and we're trying to force it into the standard form that gets a 1 over on the right-hand side, okay? When you do that, you can, if you've dealt with these before, spot exactly what your shape is without having to graph it. So here I'm going to just have to divide by 4 and have 4x squared minus y squared over 4 minus 4z squared equals 1. And then I'll write it as x squared over 1/4 minus y squared over 4 and minus z squared over 1/4 equals 1. Okay, so with respect to that, when you have that being positive 1 over there and you get it in standard form, these down here all have meaning. When you talk about ellipsoids, to be talking about the major and minor radii, but here we don't have them all being plus. We instead have two of them being minus, okay? If you have minuses and pluses here, you are going to end up with something we refer to as a hyperboloid. And this one, because it has two minus signs, there's kind of a mnemonic here, it's going to have two sheets for it, okay? All right, I am going to take, I'm going to take these and shove them over here to the side so that we have a little bit of room. And then we're going to work out here that I need to have my x, I started to say x squared, but my x over 1/2, just taking the square root there, is going to need to be equal to something. And then I'm going to end up doing something kind of tricky here, I guess. So the y over 2 equal to something, and the z over the 1/2 being equal to something, okay? So the pieces here that are minus are going to end up getting a cinch. Remember how we had x squared minus y squared equals 1, and the x was cosh and the y was cinch? So because these are getting the minus, they're going to have a hyperbolic sign, and this one will get a hyperbolic cosine. So I'm just going to come through and say hyperbolic cosine t. We might as well go ahead and make it u, right? And then the other two get a hyperbolic sine. Then breaking these two apart, the y and the z, we're going to have them doing something kind of circular. They're really going to behave as though, well, I mean, let me temporarily erase here and have, that's not going to make a lot of sense. Yeah, well, whatever. If I temporarily erase there, and if you didn't worry about the fact that they're negative, that kind of goofs things up, I know. But if they'd both been positive, then you would be looking at them together and saying, oh, that's going to be an ellipse. So with what we're doing here, we're going to be thinking about those in terms of having an ellipse. And so we will go ahead and say one of them to be cosine v and the other to be sine v. And it doesn't really matter so much which is which, okay? But now, because the u has to do with hyperbolic sine and cosine, you let it go like -1 to 1. And because the sine and cosine have to do with trig functions, we'll let them go 0 to 2 pi. If you want to go minus pi to pi, that works too, okay? Sometimes it's nice to have kind of symmetric intervals there. Well, in any case, once you have that idea in mind, then we're going to take this and just solve for the x, and take the y and just solve for the y. And can you guess? Yeah, the z we're going to take and solve for the z. Okay. And then we are going to jump over to our graphing utility, and we're just going to graph that puppy. All right. So I'm going to come in here, and for the x, what did I say? 1/2. So I'll have 0.5 times cosh u. And then for the y, 2 sinh u cosine v. And then for the z, 1/2 sinh of u sine of v. Okay. And the use, we're going to go -1 to 1, and then the v's we said 0 to 2 pi. Take that away, put it back, and you see we've got a very flat looking sort of disk there, okay? So what I really need to do is to add another graph there. And the second one, I'm going to copy things across for. And all right, and then for it, because we had the cosh being positive on the other one, we're going to have this one being negative. And then we got to make sure that our, I should have reversed U and V there. And 0, 2 pi, and 30 steps. All right, and so, all right. And so you can see there that they're stretched out in one direction and they're kind of flat looking, but we have these two surfaces. If I went ahead and told them to go, told one to go to -10 to 10 and redrew it, you can see that it would go really super dang big. But I think -1 to 1 is enough of it to get the idea. All right. So hyperboloid of 2 sheets. So can you guess that there's also going to be a hyperboloid of 1 sheet? And I think that's the next example that we got to look at. Yeah, it is. All right, so stop that sharing and jump over to the other one. And screen mirror, 1, 2, 3, go. Yay. All right. So this one, we're going to parameterize it, and then we're going to get a graph of it, and we'll see how things go. So we will have 9 times x squared. We had -54x, so it'll be -6x. Leave some space, and then minus the, oops, we'll leave that there, minus the y squared, and it had a -4y, so now it'll be a +4y. Leave some space. -9, and the z squared is a -54, so it'll turn into a +6z, and leave some space, and there was nothing over there on the other side, so yay. So we have to add 9, that means that we have to add 81, we have to add 4, that means we have to subtract 4, and then we have to add 9, meaning we have to subtract 81, so things cancel. And I have this. So you might say, oh, looks like he's got a hyperboloid of 2 sheets because, you know, I've got 2 minuses. But we have to divide, and dividing out that -4 is going to change that. We end up with x -3 squared over, I'll write it as 4/9. And then this one will turn out to be plus. And this one will turn out to be plus. Okay, so we have only one. Negative there, and so that means we're actually going to have a hyperboloid of 1 sheet. I got to tell you, I really kind of like the shape that the hyperboloid of 1 sheet draws. It just kind of looks neat to me. But we're going to write out our parameterization here, our x and our y and our z. And so our x will end up with a 3 plus 2/3 something, something, something. And the z is, or the y is a -2 plus 2 times something. And the z is a -3 plus 2/3 times something. Now we have to fill in the somethings. okay? So the ones that were positive are going to get the cosh. The ones that are negative get the sinh. So cosh t, I said t, didn't I? But we're using a u on the drawing thing. And I said one thing and then wrote another. And all right, the ones that are positive, right? And then the two that have the same sign, you're going to break up with a cosine v and a sine v. And it doesn't really matter which one's which, okay? And remember that that means that our u having to do with hyperbolics is in a symmetric interval, -1 to 1, and our v just has to have a period of 2 pi. It can go 0 to 2 pi, or, you know what, just for the sake of variety, let's go minus pi to pi on that, okay? See if it makes any difference. So, stop and turn this thing off, and, oh, hi there. I left my face on the screen, and I did not mean to do that. So, not that I'm hiding from the law or anything, just that I didn't intend to be there. Say -3 plus 2/3 cosh u sine v. Use hyperbolic. Okay, yeah, it's the same setup as before. So we get the drawing. All right. And it's drawn kind of off there to the side. So that's maybe somewhat annoying. But notice that the axis that would go down through the middle of it would be parallel to the x-axis, okay? And the x-axis is the one that gets the hyperbolic sine. So that's something that you can spot in these sometimes, all right? So hyperboloids of one sheet and two sheets are something that are relatively straightforward. But now we're going to look at something that seems like it sits between the two. In fact, it's kind of nice to maybe create an animation sometimes that shows taking a hyperboloid of one sheet and taking that neck at the middle of it and shrinking it down. And then right at the middle, you have a place where it kind of clamps off to a single point, and you have two intersecting cones. And then when you pull them apart and turn into a hyperboloid of two sheets, it kind of makes a nice continuous sort of animation. I've done that before when I had access to Mathematica, but I am not going to try it with the programs that we've got available to us right now. It's kind of neat, but it took me a day with Mathematica at hand, and I'm pretty skilled with Mathematica. So with Python, I could expect to spend a week doing it. So I don't care that much. Oh, look, I could share you my screen with the problem where we try to figure out the cone. 1, 2, 3, go. All right, so like before, we're going to look at it and try to complete the square. So 9x squared, and the minus 54 becomes minus 6x. and then minus, and the y squared, and the plus 4y. This is looking pretty similar, isn't it? And then the minus 9 and the z squared, and so it becomes minus 6z, and it's equal to 4 over there. So we add the 9, add 81, we add the 4, we subtract the 4, we add the 81, we subtract the 81. So we end up with 9 times x minus 3 squared minus y plus 2 squared, and minus 9 z, I lost track of where I was going. Sorry. Z minus 3 squared. That's all equal to 0. So if you're looking in that section about quadratic surfaces, when you end up with the 0 over there, then we have something we refer to as an elliptical cone. And so what you end up doing then is taking and putting the stuff that's negative together on one side, like so. And now it's going to have a particular form that suggests this conical sort of thing, like if you had z squared equals x squared plus y squared, which you could rewrite as z equals r, or z equals plus or minus r, I guess. And then if you did a drawing of that, it would come out fairly straightforward. But if you're thinking along those terms, then what you got to do is to take this part over here, think about it with the r stuff, and this part over here and think about it with the z stuff. So it's kind of convenient if we divide out that 9, okay, so that this portion here is kind of solved for. And then you'd have x minus 3 squared equals, and now y plus 2 squared over 9 plus, I'm going to put z minus 3 squared over 1, okay? So now you're going to have the y, I said y and wrote x, try it again. Y plus 2 over 3 is going to be equal to r times cosine theta or t. Since we've got to have u's and v's, I'm going to say u cosine v, and then z minus 3 over 1 is going to be u sine v. Because now if you work out the algebra of that, this x minus 3, you're going to end up just having the u, okay? That can be plus or minus u. So we will have x equals 3 plus u, y equals negative 2 plus 3 u cosine v, z equals 3 plus u sine v. And for your u, I'm going to tell you to make it both plus and minus, and your v, do this, the full rotation, okay? So making the u be both plus and minus is like having an r being both plus and minus. And that then allows you to draw two portions, both the upper and the lower portions of a cone. And so I have to go back there and say 3 plus u and minus 2 plus 3 u cosine v plus u sine v. And my ranges still work. Turn that off, turn it back on. And you can see that the piece that we ended up with is a cone with the axis of symmetry kind of going in the direction of this x-axis here. Okay. So you have to be able to spot when you have a 0 over there on one side that you're going to get a cone and know that that's a special case and that it's handled differently. Okay. All right. I forget how many more of these I've got. I'll get it. Yeah, I've only got like 3 more to go. So bear with me here. We are going to parameterize another one here, another quadratic surface here. That 1, 2, 3, go. Yay. This time we only have one of them. We have one of them that's not being squared. So what you will do is to solve for that one. And divide out there so that we have x squared over 1 and z squared over 4. Okay. And now essentially you're going to do the same strategy you did with the cone. We're going to have the x over 1 be r cosine. No, it's not r. It's u cosine v. And the z over 2 be the u sine v. And then the y, you just go ahead and do the squaring and putting together, and it will turn out to be u squared. Okay. So our solution here, u cosine v, y equals u squared, z equals 2u sine v, and our u, we're going to do 0 to 1. You can make it larger than that if you want to. Doesn't matter that much. And then the v, 0 to 2 pi. Okay. The reason that we don't bother with the negative is that since you square it, you're actually going to end up drawing the same thing twice. If you do that, I'm going to try on this to do the first the thing I just said, and then we'll go back and see if it looks different. We put in -1, right? I think y'all can see that fairly well there. Let's zoom in a bit more. Okay, so you can see. Now, I'm going to try changing it to go -1 to 1, and we'll see whether it turns out to look exactly the same. Keep your eye on it. Ooh, wow. It looks different, but it's super subtle. So I'm going to change it back. Watch what happens. See how some of the lines appear in the 0 to 1, but not in the -1 to 1? That's because of how it's getting broken up. Okay. And some of what goes on there, you may get some places where a surface gets written above where the juncture of two surfaces was before. I've seen this in particular happen if you go 0 to 2 pi, 0 to 2 pi on the u and v when you're parameterizing a sphere, because of where the round-offs end up landing at. Sometimes it will make the sphere look like all jagged and stuff. So, yeah. More than anything, you just have to have done a bunch of these and kind of gotten some experience with them. So, all right, another example here, and this one is parameterizing kind of an odd shape. And there's one along these lines in the classwork. Not exactly like this, but it's something that's a little bit weird. So if you think about parameterizing the portion of x squared plus y squared inside of x squared plus z squared equals 2, I kind of drew a front and side view of that, and that might not help so much. So it occurs to me that I've got a tool sitting right here beside me where we can do this pretty easily. X squared plus y squared, you'll have the you'll have it be x squared plus y squared equals 1, then you would end up having just cosine theta sine theta if it was in the plane. So you're going to go ahead and say cosine v sine v, and then for the z, we'll do the 0, or we'll do the u. All right. Now, the other one, we're going to have it be x squared plus z squared equals 1. So this one will have the u part being in the y direction instead. And then we're going to have a square root of 2 cosine u and a square root of 2 cosine. And I think that'll be okay. For some reason, it does not want to draw it. Okay. Well, that's super. All right. Can you draw it if it's complaining about this for some reason. It does not like square root of 2. It was fine with the square root of 2 earlier. Okay, 1.41. 1.41. Will that drum? It won't. Great. Okay. So you have a thin tube and you have a thicker tube that's cutting through it. So you'll have rounded tops and bottoms there. Okay. And you just have to imagine it because I can't make the computer do what I want it to. No idea. So, all right. So we're going to look here on ours. 1, 2, 3, go. All right. So we need to parameterize the portion of x squared plus y squared equals 1 inside there. So the x and the y part, because we have to be on that surface, are actually easy to do. We will say cosine u and sine u. Okay. Could have done v just as easily, but now the z, you need to make it go up and down inside of this. So we're going to think here with this x squared plus z squared equals 2. We're going to think about, can I do cosine squared u plus my z squared and get 2 there. So you know that you could have your z squared being equal to then 2 minus cosine squared u. I guess that could also be 1 plus sine squared u, but that doesn't really help too much, right? But those are going to be your cutoffs. So what I'm actually going to do is to make my z be v, okay? And then I'm going to say minus square root 2 minus cosine squared u is less than v is less than the plus square root 2 minus cosine squared u. Okay. Now, unfortunately, there is no way for me to accomplish that with the drawing program that I've got. Even if I were able to get it working right now, because of the fact that it only has your limits for the u and the v being equal to constants, right? So what you've got to visualize on this is maybe if we looked at Desmos, I think we can do that. And so jumping over here to Desmos. All right, we're gonna kill all the stuff we already had. And we had our z or our v going between minus square root 2 minus cosine, I'm going to put x, and I'm going to put the square after because this doesn't quite understand what's going on there. The notation for Desmos just does not like it when you do it otherwise. So, so that's what's going on with my z values, that they're going between these two places here. And if I go ahead and have my my x stuff, which was the u and what I wrote before, go from 0 to 2 pi, I could say x equals 0. And then I can say x equals 2 pi. Okay. And so you could see what we've got drawn there. And if you wanted a better illustration of it, I think I can do this. I can come in here and have less than or equal to y is less than or equal to, oh yeah, right. And then for my x's, I can come in here and I can say 0 is less than or equal to x less than or equal to 2 pi. Okay. So, so you can see those two intersections there. I think I chose a color that was too dark there, maybe orange. Yeah, that's not great. But maybe if I choose that to be purple. Yeah, that's a little better there. Okay, so then you have to think about rolling that around to make that surface. All right. Then I'm going to hit the stop share there. I had one more example, but I'm tired. Okay. And so if I get time later, I'll show you how to parameterize a torus, which is kind of a neat problem, but not strictly necessary for what we need. Okay. All right. And I'm going to let you go at that. This has been a super long video. I'm sorry. So.